All right. I'm going to record the second problem for the 2007 B test and see if I can work it for you. All right, so here's what I know. It says your research director has assigned you to set up the laboratory's mass spec so that it will separate strontium ions having a net charge of +2e from a beam of mixed ions. The spectrometer above accelerates a beam of ions from rest to potential difference E, MF right there, after which the beam enters a region containing a uniform magnetic field B of constant magnitude and perpendicular to the plane of the path of the ions. The ions leave the spectrometer at a distance x from the entrance point. You can manually change the EMF, and then they give you some information, so let's look at what they give you. They give you the strontium atomic number, the mass, the magnitude of the field, and the desired exit distance of x. And they want to know in what direction must B point to produce the trajectory of the ions shown. So if you come back up here, you know that the ion, first of all, has a positive charge, so I'm going to use my left hand, and it has to experience a force directed in that direction due to the magnetic field. Velocity is like that. And then there's a velocity here and a velocity here. So if you use your right-hand rule, use your palm for your force, your fingers for your field, and your thumb for your velocity. The only way that it makes any sense is if the field is pointing down into the page. So I'm going to answer the first part by saying that B must be into the page. And if I were trying to save time on the AP test, I would draw a circle and I would put an X to show them that I knew that that was into the page. All right, then part B says the ions travel at a constant speed around the semicircular path. Explain why the speed remains constant. Well, let's talk about that. If the ion travels at a constant speed, then we know that no work is done. Since KE does not change. If KE is constant, then F and B must be perpendicular. And for work to equal 0. Okay. All right. Part C says calculate the speed of the ions with a charge of 2e plus, or 2 plus 2e that exit at distance x. So what I said was, well, I know that there's a centripetal force. It's supplied by the magnetic field, force of the magnetic field. So mv squared over r must equal bqv. So I wind up with mv over r is equal to bq. And they want me to find v, so v is going to be going to be bq r over the mass. Okay, b was given to me as 0.090 Tesla. Q is twice that of an electron, so 2 times 1.6 times 10 to the negative 19 coulombs. Now the r, be careful, the radius is not x, r is half of that. 0.875 meters. 0.875 meters. And then the mass was given to us as 1.45 times 10 to the minus 25 kilograms. So if I do the math, when I did that math, I got 1.74 times 10 to the 5th meters per second. All right, and then they want to know in part D, calculate the accelerating voltage needed for the ions with a charge of plus 2e to attain the speed we calculated in part C. So I said, well, I know that the work is equal to the voltage times the charge. The work is the kinetic energy. 1/2 mv squared is equal to capital V for voltage Q. And so V is going to be the the voltage is going to be mv squared over 2Q. And so I plugged in my mass, 1.45 times 10 to the minus 25. I'm going to use that speed from part C, 1.74 times 10 to the 5th meters per second. Don't forget to square it. Divided by 2, and then divided by the charge, and the charge is 2 times 1.6 times 10 to the negative 19 coulombs. So I found the voltage. And let me see if I'm speaking truth to you. So I had my mass, my speed squared, and my 2 times 2Q, and this is Q right here. And when I did that, I got 6,843 volts. 6,843 volts. I'm going to pause for a minute and make sure I got that all. All right. So that one looks good. When I did it the second time, I actually got closer to 6,860 volts. I think that the first way I did it was a little bit funky. So I'd go with that answer right there. All right.